Hello, I'm Rozene, and in this video I will be talking to you about the simplest way of thinking about and calculating the ideal Rankine cycle, which is commonly used in power plants to generate the electricity and send it out to neighboring communities. As you can see on the picture on the right, these are the four main components of the ideal Rankine cycle, which is the condenser, the pump, the boiler, and the turbine. And a common fluid for putting through this cycle is water, and it goes through the condenser, which takes heat out of it, and then the condenser pushes it to the pump, which brings it to a higher pressure for the boiler that brings heat into it, making it hotter, and then it goes to the turbine, where the turbines use that hot water to get the necessary work out of the cycle. And the useful equations for this cycle is just the first law of thermodynamics, which is the change in internal energy is equal to the heat that is put in or taken out, subtracted by the work that is put in or done by the system. And then another equation we'll be using is enthalpy is equal to the internal energy plus the pressure times the specific volume. And the specific volume, it can also be calculated as 1 over rho, which is the density. First process we'll be looking at is the process of the pump, which is from state point 1 to state point 2, and this process is also known as being adiabatic because the heat in or the heat out is equal to 0. And so looking at our first equation, delta U is equal to Q minus W, and our second equation, delta H is equal to delta U plus delta PV. We know that delta Q is equal to 0 because the process is adiabatic, and we also know that delta PV is equal to 0 because V is the specific volume, and since this is a closed system, the specific volume doesn't change throughout it. And using this, we get delta H is equal to negative W, which is equal to H2 minus H1. And so W is equal to H1 minus H2, which is enthalpy 1 minus enthalpy 2, and Q is equal to 0 for this process. The second part of the system is the boiler, which is state point 2 to 3, and as you can see, we're using the same two equations as before, along with the assumption that the specific volume is equal to 0 because it does not change throughout the system. But this time, instead of saying it's adiabatic, we're saying that the work is equal to 0 because the boiler is only heating up the water, and so it is only adding heat into the system. And so therefore, using those equations, we get delta H is equal to Q is equal to H3 minus H2. For state point 3 to 4, we are looking at the adiabatic turbines. So once again, the heat in or the heat out is equal to 0, and we're using all the other equations and assumptions as before. So then we get change in enthalpy is equal to negative work. So then the work is equal to enthalpy at state point 3 minus enthalpy at state point 4. For the last part of this cycle, we will be looking at the condenser, which is state point 4 to 1. As you can see, we're still using the equations and assumptions as before, and this time we are also saying that W is equal to 0 because the condenser is only taking heat out of the system and putting it into the surroundings. So therefore, we get that the change in enthalpy is equal to Q, so Q is equal to H1 minus H4. And then also, once you have done all these calculations for the work and heat, whenever you add all the works together to get the work net and all the heats together to get the heat net, they should be equal to each other because this is a cycle, and so end point and the beginning point are the same, so there should be no total change in internal energy. Finally, I'll be talking about the efficiency of the Rankine cycle. So the first equation is for the Carnot cycle efficiency, which is for the 100% perfect ideal Rankine cycle, and that is 1 minus the low temperature on the high temperature. And then for the real cycle efficiency, it is 1 minus Q out on Q in. And so generally, this cycle efficiency is much lower than the Carnot ideal efficiency because of the heat that is lost due to friction in the pipes and also the heat loss throughout the system.